Hey, what's up, guys? This is Dr. Vivek Palipuram, and I'm bringing you the next lecturette in ENGR 250 Probability and Statistics for Engineers and Computer Scientists. In this lecturette, I'm going to discuss some probability theorems and axioms which are useful for us to solve probability problems, and also derive some other theorems that are more useful to derive probabilities for events that are quite complicated. So let's take a look into some probability theorems and axioms. Before we proceed any further, I would like to define certain terms which are commonly used in probability theory. And those terms are experiments, outcomes, sample space. So let's start with experiments. So an experiment consists of a procedure and observations, and the outcomes of an experiment are always random because otherwise there will be absolutely no need to perform that experiment. For example, if I take a coin and if I were to toss it once, that's an experiment which consists of the procedure, tossing a coin, and I'm going to observe some values. I can get either a heads or a tails. Similarly, if I have a die and if I roll it once, that's the procedure. And I may observe different values like 1, 2, 3, 4, 5, and 6. So that's what experiment is all about. And in science and engineering, you perform experiments of all kinds and you tend to follow a particular procedure and you're interested in what kind of observation you will have. Now, these observations will be different at different times when you perform this experiment, meaning that observations have some randomness associated with them. The next important definition in probability theory is that of an outcome. An outcome of an experiment is any one observation that you can get from that experiment. For example, if I were to roll a single die, and if I get a 4, then that is an outcome. If I get a 6, then that's another outcome. So in summary, an outcome of an experiment is any possible observation of that experiment. The next important definition that you will come across in probability theory is that of the sample space. This is one of the most important definitions that you will come across because probabilities are solved using this sample space, specifically the size of the sample space and any subsets that we consider out of this sample space. So let's define what a sample space means. A sample space is the collection of finest grained, mutually exclusive, and a collectively exhaustive set of outcomes. I repeat, so the sample space is the collection of finest grained, mutually exclusive, and collectively exhaustive set of all possible outcomes. So all of these terms, finest grained, mutually exclusive, and collectively exhaustive, have deep meaning associated with them. So let's start with what finest grain means. The finest grain means that any outcome or any member of the sample space cannot be broken into two. For example, if I were to roll a single die and if I get an outcome equal to 4, then this outcome is finest grain, meaning that I cannot construe or I cannot consider it as two twos unless I were to break this die into two parts, which becomes a totally different experiment altogether. The outcomes in the sample space are all mutually exclusive, meaning that there is no intersection between any of the outcomes. For example, if I were to roll a die and if I get a 4, that means I did not get a 6. 4 and 6 are mutually exclusive. Similarly, 1, 2, 3, 4, and 5 and 6, they are all mutually exclusive. In addition, they are all collectively exhaustive, meaning that if I were to take a union between 1, 2, 3, 4, 5, and 6, I get the sample space or the universal set for this experiment, roll a die. All of these outcomes in the sample space, they are all collectively exhaustive, meaning that if I were to take their union, I'll get all possible outcomes that can be associated with a given experiment. So that's what a sample space is. It's a collection of outcomes which are finest grained, meaning that they cannot be broken any further. They are mutually exclusive, meaning that if one outcome happens, the other outcomes cannot happen, and they are all collectively exhaustive, meaning that if I were to take a union of all of those outcomes, I'll get all possible observations with respect to that experiment. Now, here's what I would like for you guys to do. You can pause your video right here and solve this problem mentally. Roll a pair of dice, and what you need to do is elucidate the sample space, and you need to find out how many outcomes are there in the sample space if you were to roll a pair of dice. Now remember, guys, die is singular, die die is singular and dice is plural. And here we are considering a pair of dice. So if you were to roll a pair of dice, how many outcomes will be there? Essentially, I'm asking you what are the outcomes in the sample space. Moving on further, let's talk about event. In probability theory, we'll be interested in finding probabilities of different events. Now, an event is also a set of outcomes, but these outcomes are what we are interested in. So essentially, an event is a set of outcomes that we are interested in from an experiment. For example, if I were to roll a pair of dice, I can be interested in an event. What is the probability that I roll sum equal to 7? So that can happen in different ways. For example, I can roll a 1 and a 6. I can roll a 1 and a 6 and I can get a 7. I can get 2 and a 5 and I can get a 7. I can get 5 and a 2 and get a 7. I can roll 6 and a 1 and get a 7. And similarly 3, 4 and 4, 3. Where the first item, where the first number corresponds to die 1 and the second number corresponds to die 2. So these are the outcomes in my event getting a sum equal to 7. So an event is a set of outcomes, specifically those outcomes in which you're interested. In this case, I'm interested in all of these outcomes because they give me sum equal to 7. In probability theory, we are usually interested in finding probabilities of different events. So we will be looking into those outcomes that we are really interested in from the sample space. Now let's talk about probability axioms. Now probability axioms are considered as truth statements or simply truth that can be used to derive different probability theorems to find probabilities of different events. Let's start with a formal definition of what the probability actually is. Probability is a function that maps an outcome from the sample space to a number between 0 and 1. In general terms, or in much broader terms, probability is a function that maps events from the sample space to numbers between 0 and 1, meaning that events are going to have a probability value between 0 to 1. And associated with them are certain axioms, which are considered as truth statements that are considered to be true all the time. And we use these axioms to derive probability theorems that are used to find probabilities of different events. So let's start with axiom number 1. Let's say that there's an event A which will definitely be a subset of the sample space capital S, because events are always subset of sample space S. Probability of this event is always going to be greater than or equal to 0, meaning that probability value is always positive. It can never be negative. And it's true because it makes sense for us to say that the probability that it is going to rain is equal to, let's say, 0.5. It's not correct to say that the probability of raining will be negative 0.5, because what does negative 5 actually mean? Does negative 5 mean that the rain droplets are moving up? If the rain droplets are moving up, then it's not a rainfall event. In fact, it is an apocalypse. So probability values will always be greater than or equal to 0. So when you perform calculations for probabilities and should you find yourself getting a negative value, then something has gotten wrong in your calculations. Then comes axiom number 2, which states that probability of the sample space is equal to 1, which essentially tells you that whatever experiment you perform, you will get an event which will always be a subset of the sample space. For example, if I were to roll a die, I will definitely get either a 1 or a 2 or a 3 or a 4 or a 5 or a 6, meaning that sample space is definitely going to happen. So probability of the sample space is always equal to 1. So your sample space S is actually the universal set. It is the collection of all possible outcomes that you can expect out of an experiment. Axiom 3 states that, let's say you have mutually exclusive events or mutually exclusive sets A1, A2, A3, and so on until A of n, then the probability of their union will be equal to sum of their individual probabilities. Because there's no intersection between them, I can say that A1 union A2 union A3 and so on until A of n is actually A1 plus A2 plus A3 plus A4 and so on until A of n, and therefore probability of their union, A1 union A2 and so on until A of n, is equal to probability of A1 plus probability of A2 plus A3 and so on until probability of A of n. So these are the three probability axioms which are considered as truth statements, which we take it for granted that they will always be true, and using them we derive different probability theorems that are used to find probabilities of different events. Now let's start off with theorems. We'll use these axioms to construct certain theorems which will be useful for us to derive probability values for different events. Let's say that you have two mutually exclusive sets, A1 and A2, then probability of A1 union A2 is equal to probability of A1 plus probability of A2. It essentially follows axiom number 3. And this is easy to prove visually as well, because let's say that you have two events A1 and A2 and there's no intersection between them, then if you were to take a union between them, it is actually as good as saying A1 plus A2. So probability of A1 plus A2 or probability of A1 union A2 is essentially probability of A1 plus probability of A2. So that's theorem 1.2. Theorem 1.3 happens to be a generalization of theorem 1.2. So let's say that I generalize my set A to be a union of multiple sets A1 union A2 and so on until A of m, such that any two sets are mutually exclusive in this union. Then probability of A is actually sum of the individual probabilities of sets A1, A2, A3 and so on until A of n. This can be proved in the similar way as we have proved theorem 1.2. Theorem 1.4 is also important because it tells us some probabilities of null set and probability of complements. Probability of null is equal to 0, meaning that if you were to perform an experiment, at least one of the outcomes from the sample space is bound to happen, which means that probability of null is actually equal to 0. Probability of A complement is equal to 1 minus probability of A. This is also easy to prove because A complement in the end of the day is actually equal to the sample space S minus A. If you recall the definition of a complement of a set gives you another set such that any elements in this new set are not in A. So essentially I'm looking at my universal set minus A. So probability of A complement is equal to probability of S minus probability of A. Now because the universal set is bound to happen, probability of S, probability of sample space is equal to 1. So I get probability of A complement as 1 minus probability of A. This theorem is sometimes very useful to simplify certain calculations. Theorem 1.4 also states that let's say that you have two sets A and B that are not necessarily mutually exclusive, meaning that they may have a possible intersection, then probability of their union is equal to probability of A plus probability of B minus probability of A intersection B. Now what I would like for you guys to do is pause this video here and try to prove yourself why this statement is true. When you're ready, you can unpause the video and I can show you the proof of this particular mathematical statement. All right, I hope you guys had the chance to prove the statement that probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Let's try to perform this mathematically. Let's say that I have set A that looks something like this. That's my set A. And let's further say that I have set B that looks like this. So there's a definite intersection between them. If I were to consider probability of A union B, and I have these two terms, probability of A plus probability of B, probability of A corresponds to this entire region right here. And probability of B corresponds to this region right here. Now, if you carefully observe here, I have counted this intersection 1 times too many because this particular intersection is seeming to have both the violet and the blue shades. So because I have counted this intersection 1 times too many, I'm going to subtract them. I'm going to subtract it from the sum of probability of A plus probability of B. So that gives me the probability of A union B. Probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. You can generalize this for union of multiple sets with some mathematical and Venn diagram manipulation, and you can also prove that probability of A union B union C is actually a complicated looking equation, which I am going to give you for your in-class participation problem. So far, we have been talking about probabilities in terms of probabilities of events. Now, we will be interested in finding the actual probability values for the events themselves. I repeat, so far, we have spoken about probabilities of events in terms of probabilities of other events. Now, we are going to be interested in finding the probabilities of specific events. So let's start off with theorem 1.5. Let's say that I have an event B which comprises of outcomes S1, S2, and so on until S of m. Probability of event B will be equal to the probabilities of these individual outcomes. When you consider these individual outcomes, they are set within themselves. They can be considered as set within themselves. For example, S1 is a set in itself, S2 is set in itself, and so on. In addition, all of these outcomes are mutually exclusive. Now, because these individual sets S1, S2, and so on until S of m are mutually exclusive, probability of B can be expressed as the sum of the individual probabilities of S1, S2, and so on until S of m. As an example, consider that I roll a die and I further tell you that probability of any one given outcome is 1 over 6. So, probability of rolling an even number will be obtained by first enumerating what are the outcomes in this set E. So set E will have these outcomes 2, 4, and 6. So probability of event E will be probability of 2 plus probability of 4 plus probability of 6. And now if I tell you that each of these outcomes is equally likely with probability 1 over 6, then this probability of getting an even number is going to be equal to 1 over 6 plus 1 over 6 plus 1 over 6, which gives you 1/2. If I were to give you a biased die where I tell you that probability of getting a 2 is 1/2, probability of getting a 4 is, let's say, 1/6, and probability of getting a 6 is 1/12, then in that case, probability of getting an even number will be equal to 1/2 plus 1/6 plus 1/12. So that's theorem 1.5. So far, from theorems 1.1 until 1.4, we have discussed about probabilities of events in terms of probabilities of other events. Theorem 1.5 deals with the probability of event itself, and it gives you the probability of an event in terms of probabilities of the outcomes. Theorem 1.6 is actually useful to derive the probabilities of the outcomes. So consider an experiment that has a sample space S1, S2, and so on until S of n. So these are the possible outcomes that you can get from a particular experiment. Further assume that if each of these outcomes is equally likely, then the probability of any one given outcome S of I is going to be equal to 1 over n. And this is easy to prove. Now S, the set S here, in this case, is comprised of S1, S2, and so on until S of n. Now, based on the definition of a set, each of these outcomes are mutually exclusive and they are collectively exhaustive and they are finest grained. So I can write probability of set S as probability of S1 plus probability of S2 and so on until probability of S of n. Now, because each of these outcomes are equally likely, I can say that probability of any given S of I is P. In this case, then P of S, probability of S is P plus P and so on n times. Now, because probability of the sample space is equal to 1, I can write this as 1 is equal to n times P, because I'm adding P n times, which tells you that probability of any given outcome P is equal to 1 over n. So this theorem holds for those experiments where the outcomes are equally likely. For example, if I were to consider a fair coin and if I were to toss it, I have two outcomes. I can get either a heads or a tails. So n in this case is equal to 2, and therefore probability of any one given outcome, meaning probability of heads is 1/2 and probability of tails is also 1/2. Consider another experiment. Roll a fair die. What is the probability of any one side? Now in this case, rolling a fair die, a 6-sided fair die, to be more specific, n is equal to 6. So probability of any one given outcome using this equation will be 1/6. So that's theorem 1.6. There's another theorem that you can use to find probabilities of different events, and this theorem is particularly useful in those cases where you have outcomes that are all equally likely. So if you would like to find the probability of event A such that all the outcomes in an experiment are equally likely, then probability of A is equal to cardinality of event A over cardinality of the sample space, where cardinality means how many items are there in that particular set. So let's consider rolling a single 6-sided fair die, and I'm interested in finding the probability of event E, which is E is equal to even number. So the cardinality of this set E is going to be equal to 3 because event E is going to be comprised of outcomes 2, 4, and 6. Sample space comprises of outcomes 1, 2, 3, 4, 5, and 6. So cardinality of the sample space S is going to be equal to 6. So cardinality of sample space is equal to 6. So probability of event E will be cardinality of event E over cardinality of the sample space. Cardinality of event E is 3 because I have 3 outcomes, 2, 4, and 6 in this event divided by 6, giving me 1/2. So that's the application of theorem 1.A, which you may not find in usual textbooks. Now here's what I would like for you guys to do. I would like for you guys to pause your videos and try to assimilate the theorems that we have discussed using the handout which is posted on the Canvas announcement page. And then try to work on example number 1 on your own. Once you're ready, you can unpause your video and I can show you how to solve this problem. Okay, so let's solve this problem. So you roll a 2 fair 6-sided dice. What is the probability that the sum of numbers is equal to 10? So to find probabilities, usually we first start off with elucidating the sample space, if we can elucidate the sample space easily. So in this case, I need to find out how many outcomes are there in the sample space when I roll 2 fair 6-sided dice. And I can elucidate the sample space in a graphical manner for this particular problem, something like this. I'll draw 2 axes, X and Y, where X-axis denotes die 1, a number rolled on die 1, and Y-axis denotes the number rolled on die 2. On the X-axis, I can have the possibilities 1, 2, 3, 4, 5, and 6. Similarly, on die 2, I can have possibilities 1, 2, 3, 4, 5, and 6. So when I roll these 2 dice, die 1 and die 2, I can have multiple possibilities, 36 to be precise. For example, I can roll a 1 on die 1 and a 2 and a 1 on die 2 as well, or I can roll a 1 on die 1 and 2 on a die 2, and similarly I can roll a 6 on die 2 and a 1 on die 1. Similarly, I can roll a 2 on a die 1 and 1 on a die 2, and all of these possibilities. So I have these possibilities that can be rolled or that can be obtained when I roll 2 6-sided fair dice. And if I were to count these dots, I'll find that the number of dots is equal to 36. Now, each of these outcomes are equally likely. It's a reasonable assumption that any of these dots is equally likely to happen. So probabilities of all of these dots is going to be equal to 1 over 36. So probability of any one given dot is actually 1 over 36. Now my event A is sum is 10. So I need to find out what outcomes are there in this event A, where such that sum is equal to 10. So I'll use another pen color to circle those dots that give me sum equal to 10. So if I were to consider a 1 on die 1, none of these dots give me sum equal to 10. So let me find out which dots are going to give me sum equal to 10. I can get sum equal to 10 if I get 4 on die 1 and 6 on die 2. I can get sum equal to 10 if I roll 5 on die 1 and 5 on die 2. I can also get sum equal to 10 if I were to roll 6 on die 1 and 4 on die 2. So these are the possibilities. 4, 6, 5, 5, and 6, 4. So these are the outcomes that give me sum equal to 10. So these are the outcomes in this event. So probability of event A is going to be equal to the sum of the probabilities of these outcomes. So probability of event A is equal to probability of 4, 6, probability plus probability of rolling a 5 and 5, plus probability of rolling a 6 and a 4. Now, because all of these dots, all of these blue dots are equally likely with probability 1 over 36, I can say that probability of event A is 1 over 36 plus 1 over 36 plus 1 over 36, giving me 3 over 36, which is equal to 1 over 12. So that's the probability of rolling sum equal to 10. So that's example number 1. You can pause your video here and you can try to find out or try to understand how we solve this problem. All we did was we illustrated or we elucidated the outcomes in the sample space. It's a reasonable assumption to say that the probability of any given outcome is equal to any other outcome. So probabilities of all of these outcomes is equal to 1 over 36. And then we cited specific outcomes in this event A, sum is equal to 10, and we added the probabilities of those outcomes, and we found that the probability is 1 over 12. So that's example 1. Now let's look into example 2. You roll 2 fair 6-sided dice. What is the probability that the sum of number is more than 7 or the sum is an even number? So this is a little bit tricky problem than the one before. It's not difficult, but it's a little bit tricky in the sense that there are 2 events that you're looking at. You're looking at sum of numbers is more than 7, and you're also looking at the event sum is an even number. So if I were to denote sum of numbers is more than 7 using letter A, and this event sum of numbers is an even number with B, then I'm interested in finding the probability of A union B, because OR, it's a logical OR, and that translates to a union in set theory. So here you're interested in finding the probability of A union B. These 2 sets A and B may not be mutually exclusive, so it will be wise to use this formula, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. So what I would like for you guys to do is pause this video here and try to focus on finding the probabilities of A, B, and A union B, and upon which time you would have found the probability of A union B. Once you're ready to see the solution, you can unpause your video. Okay, I hope you had the chance to work on this problem. To work on this problem, I'll again illustrate the sample space for this problem using my nice graph here. So the x-axis is die 1 and y-axis is die 2. So I have 1, 2, 3, 4, 5, and 6. And here I have 1, 2, 3, 4, 5, and 6. So these are the outcomes. I can have 1 on die 1 and 1 on die 2, or 1 on die 1 and 2 on die 2, and so on. So let me take some time and quickly place these 36 dots. These 36 dots denote the outcome of this experiment, rolling a pair of dice. Okay, so these are the outcomes. Let's talk about event A. Let me use another pen color here. Let's say that I use red color. So A is sum is more than 7. So sum is more than 7. So what I'm going to do is I'm going to circle those outcomes where I find that the sum is more than 7. Sum is more than 7, let's say right here, because sum is equal to 8 now. If I were to roll a 2 on die 1 and a 6 on die 2, I get sum more than 7. 8 to be precise in this case. Similarly, I can have sum greater than 7 here and here. I can have sum greater than 7 here, here, and here. Similarly, at these points. So these are the points where I can get sum greater than 7. For example, if I were to consider this point right here, sum is equal to 6 plus 6, which is equal to 12, which is definitely greater than 7. So these red circles are those outcomes that correspond to this event A. The sum is greater than 7. Let me take some time and actually elucidate these outcomes for you. So this one here is 2, 6. This one here is 3, 6, and similarly 3, 5, and so on. There are plenty of outcomes, so I will not write all of them here. That will be too much. Okay, so in our previous example, we have shown that any of these blue dots is equally likely with probability 1/36. Because all of these blue dots are equally likely to happen, it's a reasonable assumption that one of the 36 outcomes is going to be having the same probability as the rest. So probability of event A now will be equal to the sum of the probabilities of these dots, these blue dots enclosed in the red circle. So let me use red pen one more time and write the probability of set A as the sum of probabilities of these blue dots that are enclosed in red circle. Now, because each of these dots are equally likely with probability 1/12, I just need to find out the cardinality of set A. The cardinality of set A here, in this case, is equal to the number of blue dots with red circles, and that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that gives me 15/36. So cardinality of event A is 15 because I have 15 blue dots enclosed in red circles. Cardinality of set sample space is 36 because I have 36 blue dots. Now let's talk about event B. Let me use another pen here. Let me use green pen. So event B, sum is an even number. So now what I'm going to do is I'm going to use the green pen to circle those blue dots where the sum is equal to even. So sum is even here, here, and here. It's even here, here, and here. It's even here, here, and here. Wait a second, that was incorrect. It should be here, here, and here, then here, here, and here, then here, here, and here, and then it's going to be even here, here, and here. Okay, so those are the blue dots enclosed in green circle. Now to find the probability of event B, I'll just find out how many circles or how many blue dots are enclosed in green circles. That will give me cardinality of set B. I'll perform cardinality of set B divided by cardinality of the sample space. So the number of blue dots with green circles is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it gives me 18 over 36, which is equal to actually 1/2. Let me just use 18 over 36 here. So that's probability of event B. So we have found probability of event A, we have found the probability of event B. Let's focus on probability of event A intersection B. Now, A intersection B will correspond to those blue points that are enclosed by both red and green circles. So let's find out cardinality of event A intersection B, which is going to be blue dots enclosed by both red and green circles. So that number is 1 right here, 2, 3, 4, 5, 6, 7, 8, and 9. So cardinality of A intersection B is 9. So probability of A intersection B is equal to cardinality of A intersection B, or cardinality of the sample space, which is equal to 9 over 36. So when I plug in these individual probability values in this formula, I get probability of A union B as probability of A plus probability of B minus probability of A intersection B. And if I were to do this math, I'll get 15 plus 18 is 33 minus 9 gives me 24 over 36. So that's the probability of sum of numbers is more than 7, or the sum is an even number. So those are examples 1 and 2 that showcase how the theorems discussed in this lecturette are used to solve probability problems. Now, for your Thursday's class, by 10 a.m., what you need to do is solve this problem and put it on Canvas. There will be some additional problems that you'll be submitting on Canvas. This happens to be the first one. So this needs to be solved and uploaded on Canvas by 10 a.m. Thursday. So you roll a two fair six-sided dice. So you can use the same methodology of this graph here to find out the outcomes in the sample space. What you need to find is probability of sum of numbers is greater than 6, or it is even, or both. Essentially, I'm asking you what's the probability that the sum is greater than 6 or it's even. So essentially, this problem happens to be the same as your example number 2. I would still like for you guys to solve this problem, although it is similar or exactly same as example number 2, just that the probability values will be different. Please upload your solution on Canvas by 10 a.m. I'm going to open an assignment there, which will be a platform for you to upload your work. I think it's a good time to stop this lecturette right here.